Hello, welcome to our next lecture. This one is on collisions. I'm trying a different technology, so let's see how this works. When you look at the pink questionnaires to get you through mechanics, our problem-solving decision tree, you notice that it starts with collisions. And collisions are a great harbinger of just do momentum first. No matter what the problem says, no matter what it looks like, do momentum first. So let's talk about collisions, the types of collisions, and what it all means. So the first type of collision I want to talk about is an elastic collision. An elastic collision is one where things bounce. We also need to have as a subset of our bounciness a discussion about oops, wrong pen. Sorry. With the elastic collision and the bounce, we should also pay attention to forces that are external. This is one of the things that always bugged me about collisions, is I understood when, say, two blocks are going to collide. So in the elastic collision case, I'll have one mass with a velocity colliding into a second mass and it's not moving. So I got it. When these two things went kablam, and mass 1 would go off and do its thing, and mass 2 would go off and do its motion. I got that in the middle there was this collision happening. But when it came to external forces, I kept thinking, wait a minute, I've got my usual normal force, I've got my usual weight. Don't those forces count as external? And the answer is found in our definition of the impulse, where yeah, these are absolutely external forces. But the collision time is very small, at least on the scale at which you're working. So even though you may have a normal force, a weight, maybe this collision's happening on a track that has friction, the collision itself happens over such a short time period that we don't have to worry about it. Well, all those extra forces. We will have to worry about all those extra forces in the next instant of time, but during the collision itself, we are free to use our conservation of momentum. There we go. So that means I can do my momentum of my system as a vector quantity. It's just equal to 0. A momentum in an elastic collision case we're going to have the momentum of the first object, the momentum of the second object, has to equal the momentum of the first and second objects in their initial state if I've defined this to be final. So we look above and we'll do the same steps that we did with energy, because energy, like momentum, is based on conservation. So in order to make sense of this equation, we will do our initial and final bar charts. So I've got 1, and I've got 2, and I've got 1, and I've got 2. So initially, what we see happening is mass 1 is moving some amount, and mass 2 is not moving, so it's zeroed. Momentum is a vector quantity, so when we look at the final picture, we'll notice that mass 1 is actually moving in the negative direction. And mass 2 is moving a little bit in the positive direction. So that when I subtract initial from final, I should get 0. So with this information, I can rewrite this equation as M1V1 initial has to equal M1V1 final. We've drawn it as negative, so I'll carry the negative out, plus mass to V2 final. I'd like to highlight in this situation that I don't have sufficiency. It's erasing. You B1 initial. Okay. I'm going to highlight that while I probably know everything over here, or at least it's findable, in our case here, however, in the I'm going to have to fix that. But we don't know V final for either of the velocities. And that was supposed to be NF. And then highlighted with this really horrible green I selected. So when it comes to sufficiency, I've got two unknowns that I can't do anything with. Given the fact that we don't know anything about velocity in the final case, what we'll often do is turn to familiar friends. We might be able to use kinematics if we're given enough information, or we might be able to use energy. Now, energy is tricky because we've got two masses. So when I write delta E of the system, I'm going to wind up with my system as mass 1 and mass 2, which means, as we've always done, my energy is the kinetic energy of one, the kinetic energy of the second body, plus any interactions between those two bodies, and now, of course, anything that is due to thermal motion, the internal energy of the collision. So those are all of our terms tied up with energy. It is safe, as I mentioned earlier, to ignore things like the interaction energy between 1 and 2, because it's all going to be small time intervals. But the thermal energy side, this one is going to plague us. If we are perfect in our elastic collision, then we can set this to 0. Okay, so this is a brief rundown of elastic collisions, the bouncy type. Let's turn our attention now to the next type, which is going to be inelastic collisions. I know, it's a great name. People thought long and hard about inelastic collisions as a name. For me, these are sticky. So again, if we had mass 1 moving in with some velocity into a stationary mass 2, what happens in an inelastic collision is that when we look at the final condition, the two masses are stuck together and moving with some velocity. As before, we can do a quick check to make sure we can see which terms are important. So we'll do the initial and final bar charts. And I've got mass 1, I've got mass 2, and 1 and 2 again. So this is going to look similar, except the final case is 1 plus 2. It's a single object which will carry the same momentum as mass 1 had coming in. Momentum is conserved. So delta P is, the change in momentum of the system is equal to 0. But something important happened. We turned one object became two objects. Oops, we did the backwards thing. We had two objects that became one object. One object can certainly become two or more objects if there's an explosion. Creating these, however, it's going to cost us energy to do so. So energy within our objects are not going to make us being able to use energy at all useful. Basically because, pragmatically speaking, we don't have equations we can easily plug in. So the conservation of energy exists in an inelastic collision, but it is so tricky to use that we never use energy in inelastic collisions. All right, so we finish this up with writing delta P is equal to 0, and I wind up with momentum 1 initial equaling momentum total final, and then that's just going to give me M1 V1 initial is equaling to M1 plus M2 V2 final. And in this case, if I know initial, then this is my only unknown. So very often when we do inelastic collisions, we have enough information. So one last detail I'd like to draw out before I end this lecture, let's go thick on this, is between inelastic and elastic collisions is this continuum. So in order for me to use an elastic collision, I needed it to be perfect so that I could only have my kinetic energy terms involved. A perfectly inelastic collision gives me a situation where I can write my momentum in this form. However, in reality, rarely do we have perfectly elastic or perfectly inelastic collisions. We're often at some point in between, which is just really ugly mathematically to figure out. So most of what we'll be doing is doing the extremes of this continuum. All right, see you at the next lecture.